Students, welcome to General Science 101. What we are going to do today is we are going to be looking at some graphs. What are graphs? How do we deal with them? But before we proceed to them, let us look at what we did the last time. The last time we were looking at physical quantities. We decided there were certain quantities which are physical in nature, other quantities which are not physical in nature. The physical quantities being mass, acceleration, volume, any quantity which we could measure and reproduce, and would be, the measurement would remain the same for all observers, whether I measure it in here or whether I measure it in Australia, I measure it in China, the result of all three people would be the same within the range of errors. That would be a physical quantity. For example, a length of 1 kilometer will not change whether I am in the United States or I am in China or I am, for that matter, in Australia. Non-physical quantities are those quantities which will vary when we move from one observer to another observer. For example, I might like Wordsworth's poem, The Daffodils. Another person might not like it. Now, we are two people, we are observing the same things, we are reading the same poem, but the net result or our opinions vary. And therefore, we would say this quantity, which we say is aesthetics, is not a physical quantity. Beauty is another. All the emotions we have, love, hate, you can say stupidity, idiocy, anything which two people will decide differently is a quantity which is not physical. We then looked at the types of physical quantities we have. We looked at how do we identify or how do we represent a physical quantity. We said we require four things to represent a physical quantity. We require a number. We require a number which tells us the magnitude. We require a prefix or a suffix, because a prefix or a suffix is used when large or very small quantities are used. Like a kilometer is 1,000 meters, so kilo is a prefix. We looked at, so you should have a magnitude, a prefix, a unit. A unit will tell us what quantity is it. Are we measuring speed? Are we measuring mass? Are we measuring some other physical quantity? And of course, then we have the specifications between a vector and a scalar. A vector is a quantity which also has a direction, like a force of 30 newtons towards the left, or a force of 40 newtons upwards. So it has to have a direction, or the library is 200 meters to my right. I am telling the direction, therefore it becomes a vector. Now, we have other quantities which are scalars, which do not require a direction to be identified. They are basically numbers or numerical quantities. 5 kilograms of mass, 5 kilograms of mass would remain the same. When 5 kilograms of mass is added to 3 kilograms of mass, you get 8 kilograms of mass. So basically, this is a scalar quantity. A direction is not specifically mentioned. Similarly, we have quantities like distance and displacement. Distance is the amount of walking or the movement I have done. Let us say I move from point A to point B, which is on the, but I take this path. So the total distance would be movement as I have done it. However, if we are looking at displacement, my initial position was this. When I was at my final position, it was at this point. So displacement would be in this direction only about that much. So therefore, there is going to be a difference between distance and displacement. However, both, because they are units of length, they will have a unit of meters. Same is the case with speed and velocity. A speed, for example, the example which I quoted last time is that if you move from Lahore to Islamabad along the motorway, you are going to travel a distance something like 400 and 430 kilometers. However, if you are going to travel, if you look on a map, you will see that it is 230, 280 kilometers, and therefore your speed along the motorway might be, if you are taking 5 hours, you will be traveling at something 90, 95 kilometers per hour. But if you look at your map, then you have displaced only 280 kilometers, and traveling for 5 hours would give you something like 55 or 56 kilometers per hour to the direction northwest. Same is the case with acceleration and retardation. Now, acceleration and retardation were both vectors. The only difference was acceleration, whenever we say a body is accelerating, it is accelerating in the direction of the velocity. And when we say retardation, it is acceleration in the opposite direction, or in other words, velocity is decreasing. In that lesson, we also looked at how do you add different vectors and how do you add scalars. And for scalars, we just simply said that you have to use algebraical techniques or simple arithmetic techniques, that you have 2 kilograms and 5 kilograms. The resultant is 2 plus 5 is 7 kilograms. Whereas in vectors, it becomes slightly different, because in vectors, when you are adding vectors, the resultant is the sum of all vectors. And we explained to you the head and tail rule, which we discussed last time. What we're going to be, we left you last time with 3 questions. The first question we did, and the other 2 I left for you as an exercise. What we are going to now do is discuss these questions with you. The first question which we had was that a runner on a racetrack covers 400 meters in 42.8 seconds. And we had to find the average speed. Now, the data which we have at the moment is the distance covered, which is S, which is 400 meters. We have the time taken, which is 42.8 seconds. So we have distance and we have time. And the information required is average speed. Do we have a relationship which determines average speed in terms of these 2 quantities, which is distance and time? Yes, we have. Speed is defined as distance covered divided by time taken. So the speed would be 400 meters divided by 42.8 meters, giving you 9.35 meters per second to the second place of decimal, which is acceptable as far as physics is concerned. The second numerical which we left you with, which you had to do at your home, and which we are going to be discussing today, is that a car starts from rest. There's a car which is at rest, it is stationary, it accelerates in a straight line. And we have to find, the acceleration is 3 meters per second. We have to find what speed or what velocity it has attained after 30 seconds. So in order to start this problem, we first list down what is the information which we already have. We have initial velocity is 0. That is, the object was at rest. The time taken, time is available, so t is 30 seconds. We have the acceleration available, acceleration is 3 meters per second. And the final velocity we have to find. Do we have a relationship or formula? Yes, when we were discussing acceleration in the last lecture, we said acceleration is defined as a change in velocity over time. And the change in velocity is final velocity minus the initial velocity divided by time. Now, the final velocity is what we want. Therefore, we just substitute the values which we know in the relationship. So A is replaced by 3 meters per second squared. Final velocity is something which we require. Initial velocity, which is VI, is replaced by 0. And time, of course, is 30 seconds. So what we get is 3 is equal to a VF divided by 30. Or rearranging, we find that the final velocity is 3 multiplied by 30 is 90 meters per second. When we look at the relationship of an average velocity, we still get the same relationship. Because in average velocity, we said if average velocity increases with the time, we are given acceleration. So V is equal to AT, because the initial speed was 0. And at the end of the first second, the object is moving at 3 meters per second. At the end of the second second, it would be moving at 6 meters per second. End of the third second, 3 into 3 is 9 meters per second. So at the end of 30 seconds, it will be moving at 3 multiplied by 30 is equal to 90 meters per second. So that was the question which you were to do. Hopefully you understood it. If we can always look it up again, let's look at a numerical number 3, which we left, which also was part of your homework exercise. Now, on a highway, there are 2 vehicles, car A and car B. One is moving at 22 meters per second. The other is moving at 18 meters per second. Now, we have to find the relative velocities between the two if A, they were moving in the same direction, and B, if they were moving in the opposite directions. Now, when we are looking at this, what is the information which we already have? We have the speed of car 1, or the velocity of car 1, which is 18 meters per second, the velocity of car 2, which is 22 meters per second. And we have to find the relative speed when the cars are either approaching or separating. Now, do we have a relationship? yes, we have a relationship. If the direction is the same, then the relative velocity will be v2 minus v1, because this speed minus this speed is going to give us the relative velocity. The speed of one vehicle is 22 meters per second. The speed of the second vehicle is 18 meters per second. 22 minus 18 gives an answer which is 4 meters per second. Now, in case of the cars moving in opposite directions, do we have a relationship? Yes, if we look at our list of relationships which we developed last time with you, we find the velocity in the opposite direction would be the sum of both velocities. In other words, v opposite is v2 plus v1. So because this speed plus this speed, they would be added to each other because they are either moving in opposite or they're moving approaching each other. And therefore 22 meters plus 18 meters would give us a relationship 40 meters per second. When we look at common examples, let us say that the two cars are moving together. So they are moving at the same speed. The relative speed between them is 0 because v2 is equal to v1, and therefore the speed between relative is 0, and it's very easy to pass one item from one car to the other car. This we normally see when we are watching a movie and a stuntman can jump from a moving train to a horse or a car, or vice versa, or perhaps a hero jumps from a helicopter to the train, and we do it. However, of course, don't try it at home because they are trained professionals and they, of course, are paid to do it. It still is dangerous because the wind is moving. There are other items which you have to take into consideration when you're dropping on a moving train. The train is vibrating. So there are quite a lot of things. However, for our example, the helicopter and the train are moving at the same speed. So when you drop something from a helicopter, it is going to drop directly on the train because the relative speed between them is 0. However, if we take the same example further, and there's a person traveling in a car, let's say at 10 meters per second, there's a person standing on the road, and this person throws something at that person who's standing on the road. If the person just tosses it off, in other words, the speed he imparts to some object is 0, then the only speed which is there is the speed of the car. And therefore, the person on the road will receive that object at 10 meters per second. However, if I throw it, and then the speed at which I throw would be added to the speed of the car, and the person on the road will receive it at a slightly higher speed or velocity. Now, what we're going to do today is look at a mathematical technique in which we can represent physical quantities, because in physics, we always look at the relationships between two or more quantities. What we're going to do today is look at graphs. The terminologies which we are going to discuss right now are graphs, horizontal axis, the vertical axis, a scale, proportional, directly proportional, and perhaps inversely proportional. Now, what exactly is a graph? Graph is a mathematical tool or a technique to visually show the relationship between two quantities. The quantities are always represented along axis. We have a vertical axis and we have a horizontal axis. This vertical axis is always said is the y-axis or the vertical axis. This is known as the horizontal axis or the x-axis. And the two relationships which we have, how x-axis changes with y, is the representation, a visual representation, which tells us some information. And what information is exactly conveyed, we will go on. There are different styles of graph. In physics and in biology, for example, we have a different style of graph. In physics, because we are looking at trends, we will always have a continuous curve or a continuous straight line. In biology, on the other hand, we are looking at living specimens. And therefore, the lines would not necessarily be straight. They will be from data point to data point. For example, if at point A, there were 10 living specimens, and point B, there were 8 living specimens. So we will just join the 2 points to indicate that in this range, the number of specimens were reduced from 10 to 8. Now, look at graphs. Now, when we say graphs, for purposes of this course, we will be looking at only proportionality graphs. Now, if you say a quantity is proportional, then along the y-axis and the x-axis, the quantity is going to vary at a constant rate. Or in other words, we are going to a straight line. There's going to be a straight line between x and y, and therefore, the example of course is a body moving with a constant speed. So along the y-axis, we have distance traveled. Along the x-axis, we have time taken. So if a body is moving at constant speed, the rate at which the distance is increasing has to be constant with time. Therefore, we will get a straight line which is increasing as time increases. Another graph which will give us a straight line is, of course, a body which is at rest. Because the position is not changing, we will get a straight line which is parallel to the x-axis. The distance remains constant with time. An example, of course, is a mouse resting on a table, a book resting on a table, a car at rest in a car porch, etc., etc., etc. The other relationship which we can get is a curve. We will get a curve when the relationship is not directly proportional. For example, an object falling under the force of gravity will increase its speed as it falls, and therefore distance covered in different period of time will be different, and we might get a curve which is increasing. Now, in physics, we always have a continuous curve. Another curve which we have might be a descending curve. Distance was earlier was larger, but as time increased, the distance of the displacement decreased. That is, for example, you have a car braking at a red light. Therefore, the speed before, when the driver was driving at a high speed, he looked at a traffic light, applied the brakes, and the speed went from a certain speed, let's say 20 meters per second, it came down to 0. So you would have a straight line with a decreasing curve, or you say it is a decreasing proportionality. Now, so far so good. Now, what are the steps which are required to plot such a graph? Now, whenever you have to have a graph, you have to first look at the two physical quantities you want to find the relationship of. First, you have to identify what is to be represented along the horizontal axis. B, what is represented along the vertical axis. I will not go into what is an independent variable or a dependent variable, because that might be beyond the scope of this course, but we normally take time along the x-axis and we take other quantities along the y-axis. And once I have an axis, a y-axis, I have to add there what is represented on that axis. For example, if the y-axis is distance, I have to write there this is distance, and I have to write there the units in which I am representing distance. For example, distance is represented in meter, so distance slash meters is what is going to be along the y-axis, and time in seconds, minutes, or hours along the x-axis. Then I have to select a suitable scale. What do we mean by a scale? A certain distance along the graph, what does it represent? So we have to have a scale. Normally, we will plot a graph on a graph paper. So graph paper already has boxes on it, divided into 5 or 10 equal parts, and we can always say one box represents what. On the x-axis, we can say one box will represent 1 second, 2 seconds, 5 seconds, 1 hour, 1 minute, whatever. Now, whenever we are plotting a graph, we have to be very careful. Remember, you are going to be plotting a graph so as to extract information. A graph, therefore, has to be readable. Therefore, there are certain scales which are acceptable, and there are certain scales which are not acceptable. An acceptable scale will be 1:1. One box represents one quantity, one represents 2, one represents 4, or one represents 5. Normally, we do not have one box representing 3. One box representing 3 kilometers, or one box representing 7 kilometers, or one box representing 9 kilometers. This is something which we are not going to do. Very simply, these graphs are going to be very difficult to read. When you look at a graph, visually, it is representing the relationship of quantity A with quantity B. You have to extract information from, and information should be readily be readable. It's not that I have to put a foot ruler there, measure a distance, then run up in on a calculator and find the actual value, because the scale is a very strange scale, that I have one box which is represented by 9 units, then it is going to be very, very difficult. A rule of thumb is that we normally have the box equal to a scale, which when divided, let's say if I'm saying the box is represented by 5 units, so 1 by 5 will give me a fixed number. However, 1 by 9 is going to give me a number which is never ending. It can be 1, for example, 1 over 3 is going to be 0.33333. I won't know where to stop. Normally, you only use scales in which 1 divided by that scale number should give you a fixed unit. Now, once we have decided on the scale, we write our scales, okay, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, depending upon what the scale represents, what your data represents, and we are then going to plot the different points. Let's say for 1 units along the y-axis, it is 2 units along the x-axis. We just put that point there and say, all right, we have 1 point plotted. Similarly, we plot the rest of the data points, and then we join these data points by a best line or a best curve in order to get our relationship. Now, how do you present a graph? Once we have our graph made, we have our y-axis, we have our x-axis, we have to have a suitable title. The suitable title normally in physics is what is plotted against what. This is a velocity time graph, this is an acceleration time graph, or a distance time graph. In other words, it tells us we have distance along one axis and we have time along the other axis if it's a distance time graph. And if it is a velocity time graph, we will have velocity on the y-axis and we will have time on the x-axis. Next, we have to, how do you present a graph? For a presentation of a graph, I would have to give a suitable title. What is represented in what? For example, a distance time graph should have distance and time. So I will say it's a distance time graph, a velocity time graph, or an acceleration time graph. I have to mention the scale of the graph. What does one box on the y-axis and one box on the x-axis represents? Let us say if it's the distance time graph, then one box along the y-axis is representing 1 centimeter, for example. So I will write on the top right-hand corner of the graph, one box is equal to 1 centimeter. And on the right-hand, on the bottom side, one box along the y-axis represents 2 seconds, for example. Then I have to represent on the graph what are the physical quantities I am indicating. If it's velocity, I will say the physical quantity is velocity and the units are meters per second. And the time, of course, the physical quantity is time, small t, and the units are, of course, seconds. Then, of course, I have to plot the points. My data which I have collected from any source, I will say, all right, this data now is to be transferred. So along the x-axis, 2 seconds. So how much resistance was traveled in 2 seconds? I place 1 point, 2 point, 3 points, and then I have a trend or a straight line which will join these points. Now do remember, these are data points. These are collected in an experiment, and experiment normally have some errors in it. Therefore, you will not have all points which will lie on the line. That is why we always look at trends, which we look at the best fit line. In other words, we look at a line in which some points lie above the line, some points lie below the line, some points lie on the line, and we will have an average value which will give us the trend of the graph. We can have a different type of graphs, like we said. We can have a direct or increasing proportion. If the graph starts from 0, 0, at distance is 0, time is 0, and it continues on in a straight line, like in a velocity, a distance which is being covered by an object moving at a constant velocity, I will get a straight line which is passing through the origin, and I would say it's a direct proportion. If it is not passing through the origin, that means when I started the stopwatch, the object had already covered a certain distance. Then, of course, I would say it is an increasing proportion. And when we're looking at decreasing proportion, of course, the acceleration or perhaps the velocity is decreasing with time. And the example which I quoted to you before is, I'm driving along a road, I see a red light, I press the brake, my speed decreases. Therefore, as the time increases, my velocity is decreasing, and therefore I have a decreasing proportion. You will not always get a straight line. Sometimes, if the acceleration is not constant, you might have a curve which is increasing proportion, or a curve downwards which is a decreasing proportion. So we have a body which is moving with a constant time. In a distance time graph, we would have a straight line because the distance is not changing with time. We have a body which is moving with a constant speed. I would have a straight line which is increasing. And of course, these are the graphs we look at. Now, when we're looking at graphs, we have to be careful whether we are looking at vector quantities or we are looking at scalar quantities. Now, remember, a vector quantity, like in a distance time graph, which you can see on your screens, a distance time graph, object moves, it covers a certain distance, comes to rest, then moves again because its distance, the distance time graph continue moving upward. Whereas if we had a displacement time graph and I moved towards you and then came back, I would have a graph which is represented by the one on the right, that the distance travels forward, it is increasing, I come to a rest, and it is decreasing because the object is moving back towards me. This is how we are going to be looking at graphs. Now, the graphs also give us a very good information. It allows us to form an equation. Now, in order to find a graph, we have to find the rate of change of a graph, which we normally say is the slope. A slope is defined as distance or displacement, or let's say value of y, a change in y divided by change in x is the slope of a graph. It is also known as the gradient. And as you can see on your screens, the slope is y2 minus y1, where y2 and y1 are 2 points on the graph, and x2 and x1 are 2 points of the graph. Now, in case we have a graph which is a curve, now curve is continuously changing because you might not have quantities which are directly proportional or straight line proportional. So how do you find the slope of a curve? In case, like we have on our slide, we have a graph which shows a curve at the point P. So what we do is we draw a tangent at the point P. A tangent, as you know, is a line joining the center of the curve to that point and is always at 90 degrees to the curve. So once we have a point P, at this point we have a tangent. Now we will draw a 90 degrees line to it, and we will have a curve or a straight line which represents the tangent at the point, and we will find the gradient of the tangent. Now, this is one of the techniques to find the rate of change at that point. Now, graphs also allow us to find an empirical relationship. They give us information how to form a simple equation. Now, the slope, like we defined, was y2 minus y1 divided by x2 minus x1. This is known as the gradient or the slope. Now, we know that the gradient, if I know the slope, I have the curve, then y2 minus y1 is equal to the slope multiplied by x2 minus x1. And when I rearrange it, I put in the values, it gives me an empirical relationship or a very simple equation in order to find what the information is. Now, the questions which I'm going to put to you right now are going to be 3 questions. Let us say, what is the state of a body is shown by the following figures. You have 2 figures, A and B. In one case, you have a distance on the y-axis and time on the x-axis. In the other case, you have velocity on the x-axis and you have time on the y-axis. I've asked you what are the examples, what we are looking at. Now, if we look at a distance time graph, we find that the distance is not changing with respect to time. When we see at 0, it has covered a certain distance, and as we move along, because the line is parallel to the x-axis, this graph will represent an object or a body which is at rest, which is not changing. In the second question, the question B, we have a velocity time graph. Now, if we look at the velocity time graph, again, the line is parallel to the x-axis. That means the object's velocity is not changing. It's not a distance time graph, it is a velocity time graph, and the information which you're getting out of it is that the velocity of the object is not changing with time. So this figure is going to represent something which is moving at a constant speed or a constant velocity. A car moving along a road at a constant speed will give us this graph. Now, the third question which we have is, you're given a graph in which there are 4 sections, A to B, B to C, C to D. It's a velocity time graph. And the question which we're asked is, we have to discuss the acceleration of the sections A to B, B to C, and C to D. If we look at the first section, in the velocity time graph, section A to B, we find it is a curve which is sloping upwards. In other words, it is telling us that the acceleration is increasing, because as we move along time, the slope is sloping upwards. So it is an increasing proportion. Because it is an increasing proportion, and A to B, we say the object is accelerating, because acceleration is increasing with time. When the object reaches point B, and we look at the velocity time graph, the velocity at B and the velocity at point C is at a constant rate. In other words, the velocity has not changed. Therefore, what is the acceleration if the velocity is not changing? The acceleration automatically is 0. It is the object is moving at a constant speed, or 0 acceleration. Because we had to discuss acceleration in this case, so we will say that when the object is moving from point B to C, the graph tells us that this object at that region is not accelerating, it is moving at the constant speed. So what about points C to D? Now, if point A to B, the acceleration was a positive, in other words, the slope is positive upwards, here it is negative because it is going downwards. So we would say either the object has negative acceleration, or that the body is decelerating. And that is what we are going to conclude. It is decelerating. Now, let me pose some questions. The questions which I am posing are: A, what is meant by negative acceleration and negative velocity? And I have to represent these graphically. B, the second question which I am posing to you is: what is indicated if the straight line or curve of a graph does not pass through the origin? And C, I have given you some information, data which has been collected from an experiment which gives you distances 10 meters, 20 meters, 30, 40, 50, 60, and the time taken to cover the distance. We have to state what is the type of proportion between this data. Now let us look at the 3 questions in detail, and we will now be looking at it. In the first question, I had asked what is meant by negative acceleration and negative velocity, and we have to represent these graphically. Negative velocity indicates that the displacement of an object is decreasing with time. In other words, if I am the observer, the object is approaching me, so the displacement is decreasing with time. As time passes, the object becomes nearer and nearer and nearer, and therefore we will have a decreasing line, or we will have a negative velocity, because the velocity has to be in the opposite direction. I'm not saying that the velocity is decreasing. I'm saying displacement is decreasing. The velocity will have, which is the gradient of a displacement time graph, will give a negative gradient. It tells me that the direction of velocity is opposite to where I am standing. In other words, the object is approaching me. Now, in case of a negative acceleration, a sloping downwards curve, it tells us, because acceleration is also a vector quantity, a negative acceleration means that it is opposite to the direction of initial velocity. In other words, velocity has to decrease with time, and the example which we normally quote is that a car which is going to be stopping at a red light, its velocity is going to decrease with time, because it is going to move from an initial velocity and it is going to come at lower velocity. And on your slide, I have shown to you how a velocity changes with time. You're going to negative acceleration. We are looking at constant acceleration and a constant negative velocity. Now, what is indicated in the graph which does not pass through the origin? Now, on your slide, we have shown to you a graph of a straight line which is not passing through the origin. By origin, it means it does not have a value of x is equal to 0 when y is equal to 0. In other words, it does not pass through the point 0, 0. When the value of the x is 0 and the value of y is 0, it does not pass through that point. What does this indicate? Now, if we look at the graph, we will have a slope, of course, change in y, y2 minus y1, change in x, which is x2 minus x1, which will give us the slope of the curve. Now, that small portion where it does not pass through the origin indicates that that is the position or the distance at time is equal to 0. So if I'm standing at this point and I have an object which starts, so this is a distance it has covered even before I had the stopwatch started. So that would be the initial position. Straight line which does not pass through the origin is in proportion, but it tells us that there was certain quantity available when we started the measurement. Now, what we're going to do is, in the next few minutes, try to look at how to plot a graph. You have a data. The data which is given to you is distances of 10 meters, 20 meters, 30 meters, 40, 50, and 60, and you have a time of different times are given, and we have to now plot a distance time graph, and we have to then analyze what the data indicates to us. Now, because we have to plot a graph, therefore, we have to first decide what we are going to plot along the y-axis and what is going to be plotted along the x-axis. So we take a graph paper, we draw a line along on the y-axis, we draw a line along the x-axis, telling us this is our x direction, this is our y direction. First, we write on the left-hand side along the y direction what is the quantity which is represented along that axis. Now, if we are representing distance along the y-axis, we would write distance in centimeters. In this case, it is meters. So distance is measured in meters, and we write on that quantity like I'm showing you on the section. Then we look at the units. If we look at the distance which we have, the distance goes from 10 to 60 meters. So I will have 10, 20, 30, 40, 50, 60. In other words, I have to have a graph which is going to occupy 60 units. So let us say that I will put one block is equal to 10 units. So that means 10, 20, 30. I would require 6 blocks along the y-axis. And of course, when I move along the x-axis, then of course I have a time. If I look at my available information, the time which I have goes from 0.5 to 3 seconds. Let us say that I have one box is representing 1 second. So I will use 3 boxes along the x-axis, 1 second, 2 seconds, and 3 seconds, 4 seconds, and so on and so forth. So now I have 2 x's determined. I have the x's along the y direction and x's along the x direction indicated. I will put in the x's. I will put in my scale. My scale, of course, at this moment is one box along the y-axis represents 10 meters, and one box along the x-axis represents 1 second. Then I will look at my data. The first point of my data is that when the distance covered was 10 meters, I had a time of 0.5 seconds. So my one box was 1 second. So I go to half a box, move upwards 10 meters, and I place a small x, indicating that is my data point. So that data point now represents a distance traveled of 10 meters, a time taken of 0.5 seconds. I move to the second point. The second data point which I have is at the time of 1 second, the distance traveled was 20 meters. So time of 1 second along the x-axis, I move upwards by 20 meters. I go to the 20 meters line, put a mark there, and that gives me my second data point. The third data point I have is at the time period of 1.5 seconds, the distance covered was 30 meters. So 1.5, because this is 1 second unit, it is 1 unit complete, half of a unit. I move upward 10, 20, 30. I place a cross there to indicate that in 1.5 seconds, I have a covered distance of 30 meters. Continuing on, I will plot the 2 second, 2.5 second, and 3 second marks, and now I have my data points. Taking a ruler, placing it on the data points, I discover that a straight line will cover all these points, so I draw a straight line. This straight line now indicates exactly how much I have plotted. Now I have a distance time graph available. The straight line tells me it's a straight line. It passes through the origin. So because it is a straight line, and a distance time graph is going to give you information that is distance divided by time is speed. So it gives me that it has a constant speed. The other piece of information this graph is going to give me is the rate of speed. What is the speed at which the object is traveling? Now, like we said, the distance time graph always tells us the speed. A slope of a graph is going to tell us what it is. So let us take 2 points on the line. Now, when I'm saying 2 points on the line, I do not take data points. Why? Even though I can see from my graph that all the data points lie on the line. But do remember, these are data points. Now, if I take data points as the relationship for my calculations, then that is going to cause small errors into it, very simply because the data has been gathered in terms of an experiment, and the experiment might have small mistakes. And if I take the data points, then the exercise of plotting a graph is basically meaningless, because now I require the slope of the line. I do not take the data points. I have to take any 2 points. So let us take, I'll take any 2 points. So I take a point, let's say 1.25. I see along the y-axis how much distance has traveled. So that gives me my y2 and my x2. I take another point, let us say at a distance of 65 meters, and I find my y1 and y2. And basically now I have my data points available. I have my change in y, I have my change in x. When I divide one by the other, I will find my speed. Now, let us do this question. Let's say from 65 meters to 25 meters, the time, of course, at 65 is something like 3.25 seconds, and at 25, it is 1.25 seconds. So giving me, for the 40 odd meters which I have traveled along the y-axis, displacement of 2 seconds. So 40 meters, 2 seconds. When I divide one by the other, I find a speed of 20 meters per second. So the graph which I have plotted has given me it's given me a visual representation of what the data is. When I look at the visual representation, it gives me information. Yes, the visual representation gives me a straight line. That means the velocity is constant. B, the visual representation gives me that it is passing through the origin. That means when time was 0, the object was at 0 position. It started from that point. C, the slope of the graph gave me the speed. It tells me the distance time graph, that is the speed at which the object was traveling. A straight line tells me it was a constant speed. So these are the pieces of information we can extract from a graph. The other thing which we can get from a graph is, of course, a graph allows us to predict things. Now, what do we mean by predict? Now, the graph which I have before you goes only up to 60 meters and 3 seconds. What would happen if that object continued at the same speed for another 5 seconds? I could look at the graph and extend that graph. Because it is a straight line, I can extend that line, and that I can predict that after another 5 seconds, because it is moving at 20 meters per second, so another 5 seconds, it is going to travel another 100 meters. That is a prediction from the graph. I can always look at points which are between the 2 data points. So I have one data point, I have another data point. There's a line joining them. So I can always take a point on the line between those 2 data points, and I can extract information. This is prediction. It allows me, a graph basically allows me to predict what would be the distance at that particular point of time, even though I have not extracted this information, or I have not collected that data point. Now, therefore, a graph basically allows us to predict. We have 2 data points. Whatever is happening between them, I have not extracted the information, because when I was doing the experiment, I had certain distance covered, certain timings which I took. The intermediate timing we can always predict, because it was a constant velocity. Therefore, we can predict this object would be at this particular point, and a point which is a data point which I have not extracted, but which is available from me because I have graph. I can, of course, convert this graph into an equation. An equation like, because it is passing through the region, we have s is equal to v into t, velocity which we said was 20 meters per second. So distance is going to be 20 multiplied by time. And if I have a time of 1.25 seconds, so 20 multiplied by 1.25 will give me 20 plus 1/4 of 5, 25 meters. Now, what we have done today is basically looked at a technique. It's a mathematical technique. Mathematics, when you can always look up in any book of mathematics and you'll find quite a lot of information there. But what we have done is we have looked at a technique in which we can represent physical relationships between two quantities. If we take one quantity along the y-axis, another quantity on the x-axis, and plot that, we find the relationship, how one quantity changes with another. This is very, very useful in physics, because in physics, a graph which we have looked at will tell us what exactly we are looking at, what quantity versus what quantity, how the quantities are changing. A graph also gives us a lot of other information. It allows us to form empirical relationships. It allows us to predict what if a point here and a point here, what is going to happen in that. So a graph basically allows to give us some predictions, and then of course we can test those predictions by setting up a new experiment. We looked at today different aspects of how to plot a graph. We looked at the different steps to plot a graph. Whenever we are plotting a graph, we have to be very careful what quantities we are taking along the y-axis and what quantities along the x-axis. What are the quantities we want to measure? What is the information we want to extract? We looked at the fact that we had to have a suitable scale. We have to have something which, when someone else reads that graph, does not require a lot of mathematical manipulation in order to extract information, and that the graph should give this information readily. That is why we use scales which are readily readable, and we have ratios 1:1, 1:2, 1:4, and 1:5, which are normally used in a graph. There are graphs, of course, in which we use different scales, but we are not, that is beyond the scope of this course, so we will not go into that. Then, of course, we will look at our data and we will plot the points and see whether they give us a line or a curve. Now, do remember, we have to have a continuous relationship, and therefore we plot a continuous curve or a continuous straight line, depending upon what type of graph it is. And of course, then once we have plotted a graph, we are going to give it a presentation so that it can be presented. What do we mean by a presentation? In other words, when we give a graph to someone else, the person should look at a graph and be able to extract information. The first information the person would require is, what is the graph showing? That is why we require a suitable scale. And a suitable scale, is it a velocity time graph? Is it an acceleration time graph? Or a distance or a displacement time graph? So the information tells us whether we have a vector quantity against a scalar quantity, a vector against a vector quantity, or perhaps a scalar against a scalar quantity. This is information that is going to be provided. We have to, of course, mention the scales, that what does what represent, how much if I move along the x-axis, what it is going to represent, how much if I move along the y-axis, how much it is going to represent. Then, of course, what is represented along each axis. So I have to mention what is the unit, and if I have a prefix or a suffix, whether the unit is in meters or in kilometers or perhaps in light years. Just if I'm looking at distances of stars, of course, I would have mentions of light years. And what is represented along the x-axis. Normally, if it is a distance time graph, we will have time. However, time might be in seconds, it might be in minutes, it might be in hours. The graph should give us this information. So a person looking at a graph will say, okay, this is how the experiment progressed, whether the experiment was over a period of 10 seconds, 50 seconds, or 50 hours, or some days. Then we have to indicate the physical quantities and their units: distance, displacement, velocity, acceleration, whether it's a vector quantity, whether it's a scalar quantity. Along the x-axis, it should tell us again what the physical quantity is we are plotting against. In the examples which we have taken with you, of course, we have plotted time, and therefore we would say time measured in whatever units, whether it's seconds or less. Then, of course, the graph will tell us whether it is an increasing or decreasing. You can, of course, use different colors. If, for example, the graph has got two different pieces of information, you have two cars which are moving with different accelerations. So you have an acceleration time graph, one graph showing the graph of one car, the other graph showing of the graph of the other car, you could have one in a red color, the other in a blue color, and on the right side you should have an indication telling you whether it is the red color represents the first car and the blue color represents the second car, and whatsoever it is. So that is what we have done today. We have just explored a tool, a mathematical tool, which allows us in physics to present our data better. Thank you very much, and that is all.